Hi, this is our first set of PowerPoint style notes for Chapter 5. So far, all of the material we've worked out so far, focusing on property relationships we performed on the board together. So in this set of notes, we'll talk about residual properties. I'll try and move through the material rather quickly, and we'll review it in class, and we'll have plenty of time to work through actual example problems. But we'll talk about residual properties, and one of the main motivations of residual properties will be using all of the expressions that we've derived so far. The introduction of residual properties will allow us to leverage those to calculate properties directly using a cubic equation of state. So a residual property is nothing more than the actual property relative to that of an ideal gas. So what I have written out here is we'll let f be some arbitrary thermodynamic state function. Okay, so f will be a function of two independent variables. Here we'll indicate those as being some generic variables x and y. Okay. So residual property will be indicated by the superscript capital R. So my residual property is equal to the actual property relative to that of an ideal gas. Okay. If I were to compute the differential of this expression, we would get that the differential of my residual property is equal to the differential of my actual property relative to the differential of that of an ideal gas. And if I were to integrate this expression from some state 1 to 2, we would get that the change in my residual property is equal to the change in my actual property relative to that of an ideal gas. Okay. And from the second expression, the fact that the differential of my residual property is equal to the difference of my actual and ideal gas value will allow us to leverage all of the equations that we've already derived for residual properties. Right? So we can take all of the equations that we derived so far in Chapter 5 and substitute in residual properties for our actual properties. Okay? And we'll take a look at that later on. So one note before we move on is a note on notation. Okay? So in our text, and a convention that I like or am accustomed to, is a residual property is defined as an actual property relative to that of an ideal gas. There are some books that you'll come across where they don't use the terminology residual property, but instead we'll talk about departure functions. So in general, a departure function is the same thing as a residual property, right? A departure function is nothing more than an actual property relative to that of an ideal gas. They are one and the same. The last note on notation I'll make is the superscript R is the book's notation. Notation that I commonly use outside of class is instead of a capital R, I use a lowercase res to indicate to me that it's a residual property. Okay, but again, in the chemical engineering world, residual properties are sometimes also called departure functions. That superscript could take slightly different forms. And if you were to go to the physics world, if you were to leave chemical engineering and go to physics class, there our residual properties are sometimes called excess functions. Okay, we will do everything we can to avoid that terminology because in chemical engineering, an excess function is something completely different. Okay, but a residual property is an actual property relative to that of an ideal gas. Okay. So one of the reasons that we like to use residual properties is, well, it's an actual property relative to an ideal gas. Why I like defining things relative to an ideal gas is, one, the properties of an ideal gas are well defined. Right? So we saw earlier in Chapter 5 that when we worked out, say, a differential for enthalpy with independent variables T and P, the equation nicely simplified for an ideal gas. Values of CP ideal gas were readily tabulated. We could readily calculate that ideal gas value. Okay? And so the idea is if we calculate something relative to an ideal gas, that ideal gas state is something that in general we can readily calculate. Okay, so it's defined with respect to a reference state that we can typically numerically calculate, but then more importantly, it has physical significance. Okay, so remember, an ideal gas is a system in which molecules don't interact and they don't take up space. So then physically, a residual property is going to give us, or it's going to account for the fact that molecules take up space and they interact, right? Ideal gas, molecules don't interact and don't take up space. So a residual property will give us exactly the contribution due to the fact that molecules interact and take up space. So we like residual properties because they have, a physical meaning or physical basis attached to them. And then 2, that ideal gas state is well defined, and we can typically readily evaluate it numerically. Okay. So again, the properties of an ideal gas are known. So we have our ideal gas equation of state. We've already worked out the relationship between Cp and Cv. And for an ideal gas, Z is equal to 1. Okay. We had worked out an expression in class for H with independent variables T and P. For an ideal gas, this nicely simplifies to dH ideal gas is Cp ideal gas dt. Cp ideal gas, which is only a function of T, is typically readily tabulated in handbooks that would allow us to evaluate this term. Same thing with entropy, right? So we obtain this simplified expression for entropy, where with the value of Cp, we can readily evaluate the integrals. Ideal gas, internal energy of an ideal gas is the same story. Okay? All right, so the properties of an ideal gas are well known, and typically we can readily evaluate them. Okay, so remember, if I want to calculate the change in a residual property, it's change in actual plus change in ideal gas. Okay, I integrate these expressions, I can calculate that change in ideal gas, and so to get my actual, I just need to calculate my residual. I have my ideal gas. It'll give me a link to calculate my actual value. Okay. So in terms of computing residual enthalpy, so we mentioned in the first slide that one of the motivations for looking at or introducing residual properties is they'll also give us the missing link in terms of taking our expressions from Chapter 5 and allowing us to calculate those properties using an equation of state. Okay. So here we go. All right, let's make that connection here. So here's my expression for H with independent variables T and P. For the case of an ideal gas, it simplifies to dH as Cp dt. Right? So for an ideal gas, we said that enthalpy was independent of pressure. Okay? So the trick is, we're going to define a process at constant T. So constant T then, my differential of my residual enthalpy is equal to actual relative to that of an ideal gas. Well, my ideal gas term is only a function of T, so at constant T, this is 0, and we're left with just this term. Okay, so dH residual is equal to V minus T dV dt at constant P dP. Okay, so the differential of my residual enthalpy at constant T is equal to this. Okay, so next what we'll do is, remember, a residual property is defined as actual relative to that of an ideal gas. Okay, so enthalpy in the ideal gas limit, and so remember, all fluids approach the ideal gas limit in the limit that P goes to 0 and V goes to infinity at constant T, right? So at constant T, in the limit that P goes to 0 and V goes to infinity, we approach the ideal gas limit. Okay, residual property is actual relative to that of an ideal gas. So in the case of enthalpy, in the ideal gas limit, the residual enthalpy is just 0. Okay, so the trick to evaluating this numerically is, we say, let's take this and let's integrate from the limit that, let's integrate from the limit that P equals 0 to my pressure of interest. I integrate from the limit that my pressure is 0 because at constant T, in the limit that P goes to 0, I approach the ideal gas limit. Okay, so I integrate this, integrate all of my expressions from P equals 0 to P. Okay, so that gives me HR at T and P relative to HR at T and P equals 0. Okay, so remember our process was at constant T. Okay, so in the ideal gas limit, my residual enthalpy is just 0, so this term gets killed, and we're left with just HR at T and P, and that's equal to the integral from P equals 0 to P of this term. Okay, so I can directly calculate my residual enthalpy at a given temperature and pressure as the integral from P equals 0 to my pressure of interest of this term. Okay, and this is our term that only involves PVT relationships, then in theory I can readily evaluate using a cubic equation of state. Okay, cool. In terms of entropy, we can do the same thing. Okay, so here's my expression for the differential of entropy with independent variables T and P. Here's our simplified expression for the case of an ideal gas. Step 1 will be to define a process at constant T. Motivation for defining a process at constant T is in the limit that P goes to 0 and V goes to infinity at constant T, we approach the ideal gas limit. Okay. So at constant T, this term dies, okay, as does this. So we're left with this term minus this term. Okay, and so rearranging to get rid of that negative sign, I rewrite it as R over P minus dV dt at constant P dP. So the differential of my residual entropy at constant T is equal to this. Okay, then same trick. We're going to integrate our terms from the limit that P goes to 0 to P. We integrate from P equals 0 because at constant T, in the limit that P goes to 0, we approach the ideal gas limit. Residual property is defined as actual property relative to that in an ideal gas. In the ideal gas limit, our residual entropy is just equal to 0 because our actual property is just that of an ideal gas at, the pressure of P goes to 0. Okay? So I integrate from P equals 0 to P, so my left-hand side becomes SR at T and P minus SR of T and P equals 0. Okay. This term is just 0 because this corresponds to my ideal gas limit, and in the ideal gas limit, my residual entropy is 0. So we're left with just SR at T and P is equal to integral from 0 to P, this expression. Okay. So again, this term only involves P, V, and T. So in theory, I can numerically integrate this expression using a cubic equation of state. Okay? And if I do that, that gives me a way to directly calculate my residual entropy at a given temperature and pressure. Okay? Cool. All right. So it's easier said than done, though. So if you go back to van der Waals, so the natural form of our van der Waals equation is explicit in P. Okay? If I were to go back to the equation on the previous slide, okay, that's great, okay, or especially with, enthalpy. What I would really want is an expression that's explicit in V so that I could actually work out these terms and then integrate. Okay. So these terms are, a little harder. It'd be, nice if we had an expression that was explicit in V to evaluate these. So if you look in the book, there's a couple of different ways to tackle it. One would be to go back and do our same thought exercise. So since we have these cubic equations that are explicit in P, we could instead integrate from the limit that V goes to infinity to your volume of interest, because in the limit that V goes to infinity at constant T, we have an ideal gas. Or in the text, they perform some mathematical manipulations to convert these to expressions more suitable with our pressure explicit equations. Okay, so we derived those terms on the previous slides because it's easy and straightforward. In the text, they then manipulate the equations to get them in a form more suitable to use with cubic equations of state. Okay, but it still stands that this integral only involves PVT, and so it's an expression that I could readily work out using a cubic equation. Okay, in theory. All right, so we worked out expressions for SR and HR. There's no need to work out expressions for any of our other thermodynamic friends. Okay, reason being is they're all related, right? So UR is just equal to HR minus PVR. GR is HR minus TSR. AR is equal to UR minus TSR, right? Notice I don't put an R on P or T because, well, that wouldn't make sense at all. Okay, cool. Okay, now we talked about residual properties, and one of the relationships we took advantage of in working out the expressions to calculate HR and SR and such using the cubic equation of state was in the ideal gas limit, my residual enthalpy and entropy are equal to 0. Okay, so that's also true for internal energy, but there are two exceptions. Of our friends on the last slide, the exceptions to the rule are going to be GR and VR. Okay, and so we'll take a look at those two terms and see exactly what I mean by that. Okay. So the first one is residual volume. Okay, so residual property is actual relative to that of an ideal gas. So my residual volume is equal to volume minus the molar volume of an ideal gas. Molar volume of an ideal gas, I could plug in my ideal gas equation of state. Okay, and so then collecting terms. So if I were to plug in the equation of state for real fluids here, PV equals ZRT, I could rearrange and write this as RT over P times Z minus 1. Okay, so again, for V, you could plug in, so we have PV is ZRT, so V is equal to ZRT over P, right? And so then here, you just factor. Okay. All right, so what is the residual volume of an ideal gas? So again, at constant T, so if I'm moving along an isotherm, at constant T, in the limit that P goes to 0 or V goes to infinity, I approach the ideal gas limit. Okay, so let's go through that thought exercise here. So at constant T, in the limit that P goes to 0, what is VR? Okay, so in the limit that P goes to 0 of VR at constant T, we bring out RT, and we have the limit that P goes to 0, Z minus 1 over P. So in the ideal gas limit, I know that Z is equal to 1, so my numerator is going to 0. Okay, but at the same time, our ideal gas limit is a limit that P goes to 0. Okay, so in terms of a limit, we're stuck with our friend 0 over 0. So in order to actually evaluate the residual molar volume in the ideal gas limit, we'd have to apply L'Hopital's rule. Okay, and so if we differentiate the numerator and denominator, we would get that RT is equal to the limit that P goes to 0, and we can write this as just dZ dP at constant T. Okay. So if I were to go to our Z versus P phase diagram, the residual molar volume then would be equal to the slope of my isotherm in the ideal gas limit. Okay, and the key takeaway here is the residual volume is finite. It's not 0. Okay, but it's not going to be some constant value. Okay, so residual volume is a little tricky. In the ideal gas limit, it's not equal to 0, but instead it's equal to some finite value. Numerically, it would be equal to the slope of this isotherm in the ideal gas limit. Okay, and again, all of these isotherms, just by inspection, have a different slope in the ideal gas limit, and so it's not just going to be some magical constant either. Okay, molar Gibbs free energy. So molar Gibbs free energy is another tricky one, and we'll kind of point out the issue with it here. Okay, it may seem a little unconnected. Why are we doing this? And hopefully the connection comes in Chapter 7 when we introduce a new auxiliary property, fugacity, to overcome the limitations of molar Gibbs free energy. Okay, so we're going to work with the differential of the dimensionless molar Gibbs free energy that we worked out in class. So the differential of G over RT is V over RT dP minus H over RT squared dt. Okay, so at constant T, this term, our enthalpy term, gets killed, and we have dG over RT is V over RT dP, and then here's my differential for my residual G. Okay, we're going to hold T constant because, again, at constant T, in the limit that P goes to 0 and V goes to infinity, we approach an ideal gas limit. Okay, key is that's at constant T. Okay, so if I take this expression, okay, for an ideal gas, okay, this becomes dG ideal gas over RT is V ideal gas over RT dP. Okay, plug in my ideal gas equation of state, PV equals RT. Okay, so P then is just 1 over P is equal to V over RT, and this reduces to dP over P. So if we look at the case of an ideal gas, let's integrate from P equals 0 to P. So if I integrate from P equals 0 to P, I get G over RT minus G over RT in the limit that P goes to 0. That's the integral from 0 to P, dP over P. That's equal to log P minus log of 0, which is negative infinity. Okay. So this is the result of integrating from p equals 0 to p. Okay, and so it must be then that my dimensionless molar Gibbs free energy in the ideal gas limit is indeterminate. It's equal to negative infinity. And since that's true for an ideal gas, and that all fluids approach ideal gas behavior in the limit that p goes to 0 at constant t, while we just worked out this expression for the case of an ideal gas, it must be true in general. Okay, so our issue with molar Gibbs free energy is in the limit that p goes to 0 at constant t. Our molar Gibbs free energy is unbound. It's equal to negative infinity. Okay, so then our molar Gibbs free energy, in the ideal gas limit, so in the limit that p goes to 0, is equal to actual value at the limit that p goes to 0 minus ideal gas. It's going to be equal to infinity minus infinity. Okay, so the molar Gibbs free energy in the ideal gas limit is indeterminate. Okay, so the value is, however, finite, and since ultimately we'll be interested in calculating differences in residual properties and differences in our thermodynamic properties or functions altogether, this term will ultimately drop out of our expression and is of no consequence. So as it comes to actually calculating properties, the implication of this isn't important, right? We can go and calculate properties as normal. Okay, what this will really come back to is in Chapter 7, we'll introduce an auxiliary function to overcome this limitation that the molar Gibbs free energy is indeterminate in the ideal gas limit. Okay, and so when we calculate g, we'll use our expression gr over rt is integral from 0 to p vr over rt dp, and that's 0 to p z minus 1 dp over p. All right, in case you're not convinced, so if we were to go back to our original expression for the differential of dimensionless g, the first term, which would correspond to the differential of dimensionless g with respect to t at constant p, so that's just equal to hr over rt. So we just showed that in the ideal gas limit, my residual enthalpy is equal to 0. So in order for this to be equal to 0 in the ideal gas limit, then the differential of this, so this has to be a constant, so that the differential of my constant is just 0, so that way they're consistent with each other. So this we know to be equal to 0 in the ideal gas limit, so in order for that to be true, this also has to be equal to 0, and in order for that to happen, this term has to be equal to some constant. Okay, cool. So when it comes to calculating differences in our residual molar Gibbs free energy, in the ideal gas limit, it's just equal to some constant value. So if I'm calculating differences, that constant just falls out. It doesn't matter if we don't know absolutely what that constant is, because when we calculate differences, that is a constant, and the constant cancels out of the expression, it disappears. So in terms of applications, in terms of truncated virial equation, we can use it to evaluate these expressions. We can use our cubic equations of state. There's also 3-parameter corresponding states theories, and so just like we had z is equal to z naught plus omega z1, where both our 0th order term and 1st order term are only a function of reduced temperature and pressure, we get the same thing for hr and sr. And so there's Lee-Kessler tables available to look up this H naught, H1. So as long as you know your critical temperature, pressure, and eccentric factor, along with your temperature and pressure of interest, you can use that to estimate your residual enthalpy and entropy at those conditions. Again, they're only tabulated for HR and SR, because if you have those, you could calculate UR and GR and AR easy enough. So they're going to have the same limitations as when we talked about 3-parameter corresponding states theory before in the Lee-Kessler tables. So notice those are dimensionless terms on the left. The book gives you graphs, but the appendix from Smith, Eben, and Van Ness, which is uploaded online, has actual tabulated values. In class, we'll look at using cubic equations of state in these expressions. But in general, right, as I point out, I would never actually evaluate them. Well, I won't work them out, certainly in class. Just know that in your book, the results of working out those integrals with our cubic equation state are tabulated and readily available.